train. And this is going to be a simple visual representation of a neural network. So the neural network I have here in this Desmos graph has one weight and one bias, as you can see. So it's a simple y equals x times weight plus bias. So that's the input, and then we go to that. No hidden layers. So how this neural network will train is, first, the rates are randomly initialized. So our random initialization here is giving us b equals 3.8 and w equals 1.6. Of course, I just randomly chose these, but in a real neural network, these would be randomly initialized. So then we define a number of epochs that we'd want to go through. And in each epoch, what would happen is we'd change the weight and the bias by the learning rate, which is a static parameter that we define, or non-static, but that's not important right now. So we'll change the weights and biases by the learning rate in order to make them more closely fit the data and minimize the loss. So say in one epoch, say our learning rate is 0.1. So I'll make this 3.7, and I'll make this 1.5. So then this will keep happening until we have a slope of 1 and like a bias of 1 or so. And there will be zero loss because none of these blue points and purple points are being classified wrong. All the blue points are being classified as blue, all the purple points are being classified as purple. This works with only one weight and one bias because this data set I made is completely linear. And there's not going to be any data set that actually looks like this. So this model is quite incompetent for most data sets. So how would we make this equation non-linear? So that's where hidden layers and activation functions come in. Okay, what I've gone ahead and done is I've added a hidden layer and an activation function. So the activation function I'm using for this is ReLU. So as you can see, what I'm doing here is I'm taking the max of 0 and x times w2 plus b2, so like w weight and bias. So what essentially this is doing is it's taking the output of this neuron and it's saying, oh, if this output is greater than 0, then we leave it, we don't do anything to it. But if it's less than 0, then we make it 0. So this is a simple non-linearity we can add to our neural network. And what this does is it means that we can fit our data, even though, like this data set that I've prepared, it is completely non-linear. So we don't have to just have non-linear data sets. We don't have to just use linear data sets. We can use non-linear ones. So the way I can tune this, I guess, gradient descent, what it does is it takes all of these weights and biases and it says, if increasing these would reduce the loss, or if increasing and decreasing these or decreasing these would reduce the loss, then we want to increase or reduce them by the learning rate. So what we'll do is gradient descent would go like this, reduce this weight to like 1, I don't know. And then it would go like this, reduce this bias to like 0.3. That's good. Okay, so now we fit our nonlinear data set using the ReLU activation function and a hidden layers. And this is how a dense neural network would work. So that's it for this explanation of visual explanation of neural networks. I hope you understand neural networks better from this simple explanation.